So a few final words about the ternary Goldbach conjecture. So the point here is that um, the information we have of the standard Goldbach conjecture is that every even number up to 2 to the 18, up to 10 to the 18 is the sum of two primes. And you can see how this is helpful here, because if I want to establish that some odd number up to the range of 10 to the 30 is the sum of three primes, then that affords me a lot of leeway when trying to prove that a certain given number is the sum of three primes. Because suppose that I know a prime, I mean, I have a number, let's call it n, and I want to convince you that it's a sum of it's an odd number, and I want to convince you it's a sum of three primes. Then if I can get to that number from below with a prime with an error that is less than 10 to the 18, then I'm done, because the difference is going to be with these two odd numbers is going to be an even number, and we've checked that this even number is then the sum of two primes, right? So the work done on trying to establish the classical Goldbach conjecture up to a certain limit helps here, because that means that if we want to check all the numbers until 10 to the 30, we roughly have to make sure that there's a prime every 10 to the 18, which of course there is, right? But you need to check this, right? So the point is that in order to finish the proof of the ternary Goldbach conjecture, this was done by Helfgott with Platt, you need to make sure that there's what they call a ladder of primes up to 10 to the 30, such that the distance between two primes is somewhere slightly smaller than 10 to the 18, and then you can finish the job with the experimental work on the traditional Goldbach conjecture. So that's how this works. Now let's talk about the problem by Euler, or the conjecture by Euler. As we've seen, this was shot down in a very short paper by Lander and Parkin, where they proved that Euler was wrong by finding four numbers such that the sum of their fifth powers was itself a fifth power. And so this is actually an exhaustive search done by Lander and Parkin, so they know that this is in fact the smallest example. And let me just show how that could go if you want to check that yourself. I made a program called NextList that works by saying, suppose we have a tuple of integers. I start out with 1, 1, 1, 1, and then you go on to the next list, having the property that all the numbers are integers, and also having the property that the tuple is ordered so that the biggest number comes first. So the idea is that you can sort of go through all tuples this way by starting with 1, 1, 1, 1, by saying, okay, the next one, if all the entries are the same, the next one would be gotten from taking the first entry and increasing it by 1. So that becomes 2, 1, 1, 1, 1, 2, 1, 1, 1. And then when you move on, then if the entries are not all the same, then at least one of these entries can be increased such that the value such that the list remains ordered. So here you would take the first entry and increase that to 2. You take the third entry and increase that to 2, and so on until you're at 2, 2, 2, 2. Then you increase the first one, and then you increase one at a time. So this is a systematic way of running through all the tuples of integers. Right? So then essentially, now at least in principle, you can do this as sort of indefinitely, and keep on seeing if what you have created is a counterexample to Euler's conjecture. And how do you do that then? Then you take these four numbers, you take the fifth powers, and you add them up, and then you ask, is this a fifth power? How do you figure out if something is a fifth power? Well, as we've discussed before, there's an easy way. You take the fifth root, that the fifth root, if your original number was a fifth power, then the fifth root is an integer. If it's not, then it's not. So what you can do is you can round it down to the nearest integer with the floor operation, and then take the nth power. if that takes you back to the original x, then that was indeed a fifth power, and if it doesn't, then it wasn't. Right? So I wrote is power, checking this, and then this little program here is a way of doing the experiment by Lander and Parkin. It actually turns out to take several hours, even on a modern computer. But of course, I wasn't really very clever in terms of making, or I didn't think very hard about how to make this be efficient. So this is perhaps a little bit humbling when you compare this to the fact that this was an experiment done in '66 on a computer that I'm sure is nowhere as fast as what we use today. The program works in an infinite loop, so there's no while. It just says do, end do, so it keeps on running, and then it increases this tuple one at a time and checks if this gives a counterexample, and if it does, then it breaks out and prints the tuple, and if not, it sort of keeps going. So this is one way of doing it, but of course it's not very tempting to let my computer do this right now because I know the answer and it's going to take several hours. So we are going to return to this example and see if we can do something slightly better. Now, about Euler's conjecture, then Euler had himself proved that there was no counterexample with third powers. So you're bound to ask yourself if this is true for fourth powers. Is it possible that the sum of three fourth powers is itself a fourth power? And this was shown to be the case in work by Elkies in '87. So he found the example that I'm showing in the middle. He did that by some sort of qualified guesswork, looking in a certain elliptic curve, and then finding essentially a rational solution to the problem a to the fourth plus b to the fourth plus c to the fourth is d to the fourth. And if you have a rational solution, then you can sort of cancel all the denominators that you see and get an integral solution. And this is what I've shown you here. But of course, then you're wondering if that is so I mean, that answers the question for the fourth powers. By the way, these are often called biquadrats, so the sort of repeated square. So you might be interested in knowing if this is the smallest counterexample, and in fact the smallest counterexample was found by Fry in 1988 by also an exhaustive search. Right? So just like Lander and Parkin, he goes through all the cases. This time he knows there is one, at least here, but checking all the cases, of course, takes quite a long time. This was done at this very cool computer, the so-called thinking machine, which is the sort of a supercomputer of its time, also very fancy looking. And Fry is more of a computer scientist than a mathematician, and in fact he credits Elkies for helping him with making an efficient algorithm in his little paper about this. So I would like to spend a little bit of time on how this works. So let me give you the basic ideas here. So the point is that it takes too long to go through all triples of numbers in the same naive way as Lander and Parkins did for the fifth powers. And there's various little tricks you can make by sort of looking at some number theoretic properties of the problem that you're looking at. And the first thing you can see is that suppose you look at all the biquadrats or fourth powers of remainders mod 5, then they are of a very special form. So I've computed 0 to the fifth, 1 to the fifth, and so on up to 4 to the fifth. To the fourth, up to 4 to the fourth. And what you can see easily is that mod 5, these are either 0 or 1. So this tells you something quite useful about this equation here, because if you have an equation with a, b, c, and d, if you have a solution with a, b, c, and d, we're after the smallest solution, right? We just want to find the smallest solution. So then by looking at this mod 5, that sort of tells you something about what can happen here. Because if more than two of these numbers are 1 mod 5, then you cannot have a solution, right? Because, for instance, this is 1.5, this is 1 mod 5, this is 0 mod 5, then what you have over here is 2 mod 5, and we know that cannot happen for a fourth power. So that means that the only way you can have a solution is that either everything is 0 mod 5, or you have 1 mod 5 and 1 mod 5 here, and then 2 zeros mod 5. And of course, A, B, and C occur in a symmetric fashion, so you don't have, you may as well assume that it's A that is 1 mod 5. Now, the one with only zeros you can forget about, because if you have only zeros everywhere, this means that 5 divides all these fourth powers. Well, then 5 would have to divide also A, B, and C, and D, and you could divide through by actually not just 5, but 5 to the fourth, which is 625, and you would get a smaller solution, right? So that's not the smallest solution. The smallest solution must have the form one of the values is 1 mod 5, and the other two are 0 mod 5. And D has to be 1 mod 5. So that already makes the search space a lot smaller. We can assume that A is 1 mod 5 and B and C are multiples of 5, and so we can save some time